All right, in this video lesson, we're going to go over one example of three. So these are examples that you could potentially see on worksheets or tests or quizzes. So let's go ahead and take a look at what's going on here. A 5-kilogram box is sitting on top of a table, and it's initially compressed against a spring that has a spring constant of 25 Newton per meter. The box pushes the spring in 0.32 meters. The box is then let go and it slides across the tabletop. After about 2 seconds, the box has lost 20% of its energy to E dis, or in other words, to friction. How fast is the box moving at this point? Draw bar charts before you solve. And actually, in fact, before we draw bar charts, what I would like to do is just draw a picture of the situation so we know what's going on. So we have on top of a table a box that is actually being compressed against a spring. Then what happens is the box is let go, and sometime later, we're told 2 seconds, the box is moving across the table, and it's lost some of its energy to dissipated energy, or friction. So now that we have an idea of what's going on, we have our initial spot, and then our spot sometime after, which is 2 seconds. We're now going to draw our bar charts. Let's think about the initial situation when the box was being compressed against the spring. What energies would be there? Well, Eg wouldn't be there because it's not elevated to any sort of height. It's on a level tabletop. There's no Ek because the box hasn't been let go. And you will never have dissipated energy in the first bar chart. Dissipated energy comes after the fact. So by process of elimination, we can see all of our energy must be elastic. Since I haven't calculated anything, I'm just going to make it qualitative for right now. I'm going to make my bar chart go up 7 squares to represent my total energy. Now, in the next bar chart, this is going to represent 2 seconds later. At that point, is the box up in the air or has it elevated in height? It hasn't, so there's no Eg. The box is moving, so we'll have kinetic. At this point, the spring has become uncompressed, so there's no longer any elastic energy at that point. But we are told that there's some dissipated energy. Some of the energy has been lost due to friction. Now, I'm going to not worry so much about making my boxes 80% and 20%, but instead I just want to show that kinetic is the majority, and then the dissipated is only a little bit. 20% is only a little bit of the energy. When we start calculating and getting some actual numbers here, we can then get more specific. Okay, so now that I've got my bar charts and I've made my bar charts equal each other because I want to show energy is conserved, let's go ahead and start solving the problem. The first thing I'd like to figure out is I would like to figure out what is the total mechanical energy in my problem. I can figure out the total mechanical energy from either bar chart, provided I have all the information. The most obvious one is probably going to be find out the energy from the first one, because the first one I only have to deal with elastic energy. And elastic energy has the equation of 1/2 kx squared, k being the spring constant and x being the distance that the spring is either stretched or compressed. In this problem, we are told that my spring constant is 25 newtons per meter. Let's make sure we understand what that means. What that means is it takes 25 newtons if we would like to stretch or compress the spring 1 meter. All right, and then we are told the x, which is the amount that the spring is deformed, is 0.32 meters because it's pushed in. So 0.32 meters squared. If I calculate this out, 25 times 1/2, and then times 0.32 squared, I end up getting the energy is 1.28 joules. So this is my total mechanical energy, meaning that that must be the total energy that is in the entire problem, no matter what stage. So that tells me in bar chart number 2, the kinetic energy and the dissipated energy must total 1.28 joules of energy. Now we're told at 2 seconds later, 20% of the energy has been lost to E dis, or to friction. So what is 20% of 1.28 joules? Well, we just take 1.28 times 0.2. If I do 1.28 times 0.2, I end up getting 0.256 joules. This is the amount of energy that is lost, or E dis. So that means my kinetic energy must be 1.28 minus that. So 1.28 minus 0.256 gives me a kinetic energy of 1.024 joules 2 seconds later. It's this energy that I'm going to use to figure out how fast the box is moving. So I'm going to take 1.024 joules of kinetic energy and set that equal to 1/2 the mass of the box, which I'm told is 5 kilograms, times v squared. And I'm going to go ahead and solve for v. If I do 1.024 divided by 1/2 and divided by 5, I end up getting 0.4096 is equal to v squared. Square rooting both sides ends up getting me my velocity at that point of 0.64 meters per second. This concludes the video lesson on the first example.